In this example, we are going to look at the reading of a Geiger-Müller counter and how it contributes to our understanding of radioactivity. So right behind me, you will see a setup of a Geiger-Müller counter. This is more towards the lab, not the handheld type. Right, and you can see that there are slots here, and we can place different radioactive sample inside the slots to measure the Geiger-Müller counter. Okay, so these are the sample. So if you want to know how a GM counter works, there's an article here. You can Google a bit. But the whole idea is whenever ionizing radiation passes through the counter, it will ionize the air particles inside, and then that ionizing will cause a spark. Okay, so if you're interested in what they call this ionizing avalanche. All right, but in this particular example, we are going to look at the actual reading of this Geiger tube with respect to time. All right, so I'll show you the graph now. Okay, behind me, you will see the graph. This is a count rate graph against time measured in hours. All right, and so you might be thinking, this graph looks very weird. Why is it so zigzaggy and inconsistent? You know, well, I have a simulation for you to show you how these zigzag graphs come about. All right, there are many reasons that contribute to this slightly random and inconsistent readings. So what I have here is a model of some radioactive nuclei. Red means still radioactive, haven't decayed yet. And then we're going to plot the graph of the number of radioactive nuclei starting with 100, and then it will go down, and then already decay one will go up. Let's see. So you will notice that there are like some zigzag patterns because this pattern is random. So if you look at this pattern, right, and if I repeat the experiment again, we won't get the same pattern one. Okay, let's see. Once again, you notice that the shape is slightly different. All these zigzag patterns are, I mean, it's not zigzag, but these patterns are not the same at all the time because of the random and spontaneous nature of the decay. Look at this. This looks so different, right? Okay, so this is probably why we get this kind of shape. Okay, but let's start off with the question first. This question is from Winter 17, paper 41. Okay, so a radiation detector is placed close to a radioactive source. So if you think back about the picture that I've shown you just now, this is the radioactive detector. Okay, and we're going to put the source here. Right, so we're going to register the counter and allow the sample to sit inside there maybe for a few hours. Okay, so the detector doesn't surround the source. So basically what we have is probably something along the line of like having a detector like this. So this is the detector and the source is here. All right, so there will be some ionizing radiation that will cause that spark that happens inside the detector, but it doesn't surround the source. So radiation is emitted in all directions. So if I'm going to draw out the particles, the radioactive particles that come out, it's going to come out in all directions. So it's not able to pick up everything that comes out. Ideally, the detector should be wrapped around this sample size. Okay, so as a result, the activity of the source, the actual activity, and the measured count rate are different because maybe we can only measure this one. Those who travel in opposite direction cannot measure already. No? So suggest two other reasons why the activity and the measured count rate may be different. Well, the first thing that you can say is there is definitely some background radiation. Okay, there could be some background radiation because radioactive particles exist everywhere. It's just that they are not that common, but there's always background radiation. Okay, you could say that the window of the detector, so there's a mica window here. Okay, so this window, the window of the detector may absorb some of the radiation. May absorb some radiation. Okay, so these are probably reasons. Other reasons could be absorption in air, so always blame absorption. So maybe the air will absorb, especially if it's alpha particle. So absorption in air before reaching detector. Okay, so these are all a few different reasons, but the background radiation one is the most common. Okay, let's look at part B. The variation with time t, the count rate is shown like this. So I've explained just now why we get this kind of zigzaggy pattern. All right. State the feature in this graph that indicates the random nature of the radioactive nuclear decay. So you can say the curve is jagged or the curve is not smooth. All right. So this is how you know that this is random. You get that beep, 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 beep. And maybe if you run the experiment again, you will get a slightly different picture. But you can see the trend is still kind of the same. So if I actually draw the trend line for this particular graph, let me draw this in gray. You can probably get a graph that looks a bit like this. So again, just roughly sketching out the trend line, aka best fit line. Okay, so you can see there's a extra. All this extra is probably due to the background radiation, and also because sometimes the decay is random, so sometimes the decay will fall below the trend curve. It's all good. Random, that's why you get that jagged line. Okay, next. Use the graph to determine the half-life. So we're gonna determine the half-life of the radioactive isotope in the source. And please note that this question is 4 marks. Okay, to account for background radiation, we need to look at the whole graph. And notice that this graph kind of plateaus here. Okay, let me zoom in. Notice here it kind of flattens out, it plateaus. All right, so when the graph plateaus, what this tells us is that the decay is almost zero already. So I can treat this entire 2.5 boxes, roughly, here to here, this 2.5 boxes, as background radiation. All right, background radiation. Because you can see from 10 hours onwards, it's just kind of sitting at 2.5 boxes for like 4-5 hours in a row. So it's pretty good. 1, 2, 3, 4. Yep. It's been sitting at 2.5 boxes. So because of this, all the readings I can assume has a systematic error of 2.5 boxes. Okay, so in terms of count rates, 2.5 boxes is 10. All right, so we have to shift the graph down by 10 or shift all the readings down by 10. Okay, so if I'm going to zoom in here a bit and look at the initial reading kind of looks like 170. So if you look at this curve here, this part of the curve, right? It kind of looks like, okay, maybe you can't see blue, give it a sec, orange. It kind of looks like this part of the curve. This part looks close to, I mean, it's hard to tell, but it kind of looks like 170. Okay, but remember background radiation. So background radiation means we have to bump it down. Background radiation is like systematic error. When your reading is supposed to be 0, you didn't get 0. You get 10 or 2.5 boxes, meaning all this reading is bigger than the real value by 2.5 boxes. So sneaky, right? So we have to shift this down, and this reading is actually 160. So the half-life of 160 is 80. 60 by half is 80. But 80 is not actually 80. To find 80, we need to add back the background radiation. Okay, so the background radiation is going to be 90. So I think 90 or 2.5 boxes is kind of sort of somewhere here. Okay, so we will minus 10, and this will give us 80. All right, so when we take half-life, the actual reading from the graph perspective, it looks like you are taking from 170 to 90. But actually what you are taking is 60 to 80. Okay, so I'm going to just write that down somewhere for the people. Okay, so the reading for half-life is 170 to 90. So this one doesn't feel like it's count rate because we haven't subtract the zero error yet, or the background reading. Background reading is 10. So if you subtract 10 on both sides, then we are actually taking from 160 to 80, and this is my half-life. Okay, so we have to take from 170 to 90 because of background reading. So if I'm going to read this reading, this first half-life, from here all the way to here, it kind of looks like, let me see, 1.6 hours. So I'm just going to put 1.6 here. Okay, so this is my half-life. From the perspective of the graph, you are taking 170 to 90. But because of zero error, or background radiation, is a systematic error, 170, the real reading is 60, and 90, the real reading is 80. Go repeat again for another half-life. So after 80, half of 80 is 40, but we're not going to take 40, right? Because now we're going to look at the second variation of the reading. We are now going to take 90, 92. So we wanted to take 80 to 40, but that is without background reading. So what we wanted was 80 to 40. This is what we want. But we need the background reading. We need to subtract the background. So what minus 10 is 40? 50. So we're going to have to take 90. So this one is 90. Okay. This is 90 to 50. All right. So let us look at where 50 is. 50 is kind of here-ish. So I would say 50 is here. Okay, right in the middle. Not sure if you can see. Okay, so I'm just going to dot here. This is 50 lah. All right. So that would be time interval between these two lines. This is your half-life. So by counting boxes, where 5 boxes is 1 hour, and this is 1.5 cm. So 1, 2, 3, 4, 5.5. So here to here is 1.5 hours, 1.5. Okay, so you have 2 half-life readings already. So the reason why we want to take 2 half-life reading is because, number one, this random nature of the decay curve, the zigzaggy nature, okay, means that there's some form of random error already. So it's better to take repeated reading. Okay. Number two, because of background radiation, these 2.5 boxes, there's always systematic error. And to account for systematic error, meaning all the readings you take have to minus 10 or have to minus 2.5 boxes thanks to the background radiation. So instead of 170, it's actually 60. Instead of 90, it's actually 80. So 160 to 180 is 1 half-life. Okay, again, instead of 40, so instead of 50, it's actually 40. So here to here is another half-life. Okay, so we are accounting for this. And to make sure that the examiner know what we're doing, I'm not just going to have the label here. I will try to write it out clearly first for us. Let me get ourselves to the page and zoom out a bit. Okay. So first thing I'll do is I'll announce the background radiation. The background radiation. Let me make it just a little bit. Background radiation is 2.5 boxes or 10 counts per minute. Okay. So this is a systematic error. Systematic error. Okay, so that means your reading is always over by 10 counts. Systematic error. Am I spelling systematic correctly? No, that's no H. Systematic error. Okay, so number one. Number two, because number one is 4 marks, number two is random. So we're going to take 2 readings. Reading 1, we will take the count rate of 172 or 170 minute -1 to 90 minute -1. This is the detector reading. But actually, the real reading is 160 minute -1 to 80 minute -1. This is real reading. Why is this the real reading? Because of these 10 counts per minute. So when we go here to here, -10. Go here to here, -10. You have to minus the background radiation. You don't have to draw this purple arrow. I'm drawing it for you. Okay? So we're going to do, so hence the half-life is 1.5 hours. Right, that was our first reading. Repeat again. Number 2. Reading 2. So reading 2, we took 90 minute -1 to 50 minute -1. This is detector reading. Okay, the real reading was 80 minute -1 to 40 minute -1. This is the real reading. So hence, from the graph, this half-life was 1.6 hours, I believe. Okay, so once we have these two readings, but let me double check first. Is it 1.5 and then 1.6, or is it 1.6 then 1.5? 1.6 then 1.5. Okay, my bad. Hang on. 1.6 then 1.5. 6 hours, 1.5 hours. So you have to find the average, right? You have two repeated reading. So step 1, step 2, step 3, and step 4. Average of half-life will be equal to 1.6 plus 1.5 divided by 2. So your answer is 1.55 hours. All right, you may be wondering where the marks are. 1 mark is when you account for background radiation. So here is a lot of evidence that if you write like this, there's ample evidence to show the examiner that you're accounting for background radiation. Number 1, you took the background radiation reading. Number 2, you show the subtraction between the real and the detector reading. So accounting for background is 1 mark. Okay, 1 mark is for repeated reading. Okay, 2 marks is when your half-life is between 1.4 to 1.6. So this is our one is correct already. The other mark is when your half-life is between 1.7 to 2.0. So this one got range 1. If you get between 1.4 to 1.6, you get 2 marks. But if you get between 1.7 to 2.0, you only get 1 mark out of 2. So totaling to 4 marks, no? Can? Okay. So the accuracy matters. And this is how you account for background radiation. What did we do? Number 1, we look at where the graph plateaus, which is here. When the graph have already plateaued, this means that the background radiation is whatever reading that you take, because this one is supposed to plateau to close to 0, but it didn't. So this means that whatever background radiation that we have here, okay, is 2.5 boxes. So all this, whatever reading that we have to go down by 2.5 boxes, go down by 2.5 boxes, which is 10. Basically, all the readings we subtract by the systematic error. All right, so hopefully that is clear. I'm going to move on to part C now. Okay, part C. The recordings in B are obtained at room temperature. Okay, very nice. We got this reading on room temperature. The second sample of this isotope is heated to 500 degrees Celsius. Okay, we increase the temperature of the sample. Initial count rate at t equal to 0 is same as B. So that means we have the same sample. The variation with time t and the measured count rate of the heated source is determined. So basically, we repeat the identical experiment. The only difference here is we increase the temperature by 500 to 500 degrees Celsius. What happens? If there a difference, state with a reason, the difference, if any. So we need a reason. Don't just say increase, decrease, constant. So let's think about the half-life. You understand that this entire reaction is random and spontaneous, right? So because this is spontaneous, it is independent of environment. So the half-life will have no change. Okay, you can say that this is because nuclear decay is spontaneous and independent on environment. Okay, so no change. Number 2, measured count rate at any specific time. So remember your graph? It looks like this, very zigzaggy, and that one zigzag. So let's say I take this any particular time here, dot. I repeat the reading. Will I get back the same time? Well, if you remember this sample that I show you, let's say we take this point here lah. We see this steep point. Okay, let's take one of these points here. Okay, let's say at 40. This 40, this is about 2.5 hours. If I repeat the experiment, will I get exactly the same reading? No. 40 is now slightly less than 2.5. You can see that the graph is not the same. So because of this, right, the count rate is likely to be different. Okay? And then the reason would be because the nuclear decay is random and cannot be predicted. Over time, you will have a certain trend. But right now, if you want specifically at that particular time this will happen, it's asking too much lah, okay? Because this is a distribution. All right, so this is the question. These 3 marks here would be 1 mark if you say no change. 1 mark is when you say the decay is spontaneous or doesn't depend on environment. The second one would be different because of the word random. Okay, so this is a pretty straightforward question. Basically, the entire question is asking you whether you understand the nature of detection of radioactive particles. So, for example, how the detection could be faulty due to various errors, like background radiation, and maybe there's some absorption due to the materials around the experiment. Okay, maybe air, maybe the window of the detector. From the zigzaggy graph, we can see that this thing is random. And because it's random, we can very, very low chance to get back the exact same reading at that exact same time because it's random. Okay. And then number 2, there's background radiation. So 2.5 boxes have to remember to minus. So it's just asking you whether you know what causes the fluctuation, what is random, what is spontaneous, and how to estimate half-life, especially when you have background radiation. Okay, so that's it for the question. I hope you learned something today, and I wish you all the best in your A2 studies. Share this video with someone. Let us ace our A2s together. I'll see you in the next example. Peace out. Bye-bye.